Hello guys, welcome back to my channel Gamma Die Gamma. And in this video, we'll be specially tackling an integral that involves the error function. And mind you, it's an improper integral. So as always, let's get started. Okay, so the problem at hand, let's call it I as always, is the integral from 0 to infinity of the error function of x squared divided by x squared dx. Okay, it just might seem nonsensical to some of you who haven't seen the introducing the error function video. So please check that out if you haven't already. But in any case, I'll recap. So we know that the error function of x is sort of a generalization of the Gaussian integral, but normalized. So 2 over square root of pi times integral from 0 to x of e to the negative t squared dt. So it's a function that actually involves an integral, and this is really helpful when it comes to a distribution and like statistics and stuff like that. Okay, fair enough. But okay, this is like a general background, but how is that actually helpful when we are actually trying to calculate this integral? Because notice we have a polynomial in the denominator and this weird complicated function in the numerator. So if you go by your intuition that says that polynomials of lesser degrees are more favorable when it comes to integration, you're going in the right direction um, because there is actually a property we can use to reduce the power of the polynomial in the denominator. That technique is called integration by parts. And what are we going to differentiate? What are we going to integrate? Well, one way to think about it is this error function already involves an integral. So taking the antiderivative of that is going to be really cumbersome and not worth it if you ask me. It's just, complicating the issue even more. So might I recommend integrating this denominator polynomial while we differentiate this error function. Okay, and this goes well with our intuition that says we have to reduce the power of the polynomial, because if you integrate 1 over x squared you end up with negative 1 over x, so you effectively reduce the power, the absolute value of the power. So from being 2 in the denominator we have 1 in the denominator. So slight improvement there. But if we're going to differentiate the numerator, we need to find the derivative of the error function. So derivative with respect to x of error function of x is naturally 2 over square root of pi times the derivative with respect to x of integral from 0 to x of e to the negative t squared dt. And trust me, this is a really complicated derivative, more complicated than we are actually used to deal with. And to actually tackle with such a derivatives of integrals which involve, whose upper bounds involve the basis of differentiation, there is actually a rule, and that rule is actually called Leibniz rule of differentiating under the integral sign. So a general statement of this rule says if you have the derivative, say d over dx of some antiderivative expression which has lower bound, say f of x, upper bound g of x, and I don't know, some arbitrary function, call that capital H of x. Let's have another value, t dt. So by the Leibniz rule, that is going to be integral of f of x g of x, but the partial derivative with respect to x of h of t dt, but plus h of g of x times the derivative with respect to x of g of x minus h of f of x times the derivative with respect to x of the lower bound f of x. And this is actually the entire essence by which we have our method of the Leibniz rule when we are integrating non-elementary integrals. It's just that in those cases, the upper and lower bounds don't depend on x. So these two terms, these plus and minus terms without the integral sign, actually go to zero because the derivative of a constant with respect to x will be zero. But this is the more general case where the upper and lower bounds depend on x, or the variable of differentiation. And we're actually going to apply the same thing because notice the upper bound depends on x. So we're actually going to have to apply this. Okay, so back to our business of differentiation. We have the derivative with respect to x of error function of x is equal to, well, 2 over square root pi. Then we have integral from 0 to x of uh, partial with respect to x of e to the negative t squared dt plus e to the plug in the upper bound in the place of t, so e to the negative x squared times the derivative with respect to x of x, because that's exactly what the upper bound was, minus e to the negative 0 squared and the derivative with respect to x of 0. So this term will go to 0, and since uh, e to the negative t squared is only a function of t, not a function of x, even this will go to 0, just giving us finally derivative of x with respect to x is 1, giving us 2 over square root of pi, because that was actually a constant. I forgot to bracket everything out. 2 over square root of pi times e to the negative x squared. That's the derivative with respect to x of the error function of x. Pretty neat, isn't it? And that's why it's really nice to have to differentiate the numerator while we integrate the denominator. So now, by integration by parts, I is equal to, well, integrate the denominator, so we have negative x, and keep the numerator, the function we need to differentiate as it is for now, evaluated from 0 to infinity, minus integral from 0 to infinity. This minus and the minus from the antiderivative will cancel, make a plus. We have x in the denominator, but the derivative of this, now we'll have to use the chain rule, is 2 times error function of f of x times the derivative with respect to x of the error function of x dx. Okay, so this becomes negative error function squared of x over x from 0 to infinity plus 2, and we also have this 2 from the derivative, so 4 over square root of pi times integral from 0 to infinity of error function of x times e to the negative x squared over x dx. Okay, we'll actually call this I1. Let's first deal with this limit thing over here. So when I plug in infinity, so we have minus limit as x tends to infinity of error function squared of x over x. So noticing the original error function that we defined, if you let x go to infinity, you'll have integral from 0 to infinity of e to the negative t squared dt, which is exactly square root of pi over 2. So we have 2 over square root of pi times square root of pi over 2, which will be 1. So in the limit as x tends to infinity of error function of x, you'll have that going to 1, and even the square of the error function is 1 squared or 1. So you have 1 in the numerator and x is going to infinity, so the denominator is getting really large, making the entire fraction go to 0. So we don't need to worry about the infinity part. Now for the 0 part, so we'll have error function squared of 0 over limit as x tends to 0 of, say, x. Don't call this 0 as of it, call this x. Make a limit subtend to that. Okay, so if you look at your error function, if x is 0, so you have integral from 0 to 0, which, if you know your fundamental theorem of calculus, will be 0. So we have a 0 on top and a 0 in the denominator. So 0 by 0 case, which means we can apply L'Hopital's rule. So quickly doing that, we have limit as x tends to 0 of differentiate the numerator 2 times error function of x times the derivative of the error function, which is 4 over square root pi times e to the negative x squared. And the denominator derivative of x is 1, is just 1. So error function at 0 is going to be 0. E to the 0 is 1. So 0 times 1 times some constant is still going to be 0. So even for the lower bound, this will be 0. So entirely this term will go to 0. So our integral that we were concerned with is just going to be equal to I1, which is 4 over square root of pi times integral from 0 to infinity of error function of x times e to the negative x squared over x dx. Now this is going to require a little more work, so let's tackle this on a fresh page. See you then. Okay, so as discussed previously, we have I1 equal to this. Now what I'm going to do is I'm going to rewrite the error function in terms of its definition. So we integral from 0 to infinity of e to the negative x squared over x. Now the error function is integral from 0 to x of, take another variable, e to the negative t squared dt, but it's also accompanied by this factor of 2 over square root of pi, and we have a dx. So now what we're going to do is take the constant outside, so 8 over pi integral from 0 to infinity of integral from 0 to x of, well, e to the negative x squared e to the negative t squared over x. You have a dt dx here. Okay, now just use some exponential properties. Club this to e to the negative x squared plus t squared over x dt dx. You know, instead of having a t, why don't we call it a y? Just for the sake of, you know, x and y as the axes, the variable of the axes. And this is really important because we have x squared plus y squared on top here, you know, raised to the in the power of e. So, and the dy dx here. So this is actually a legit double integral, a legit double integral. I don't know how long it has been since we calculated one like this. So for this, what we're going to do is actually just use spherical coordinates because we have x squared plus y squared, and stuff that resembles the Pythagoras theorem actually calls for polar coordinates. So now converting to polar coordinates, so going polar, we know that x is equal to r times cosine theta, y is equal to r times sine theta, and we know dx dy by the determinant of the Jacobian is r dr d theta. Okay, so we know all this, but how will our upper and lower bounds change? And in higher order integrals, the upper and lower bound are the key. So let's draw an image. So let's take this inner, let's just consider this inner integral over here, which I've bracketed. So on this inner integral, only look at the upper and lower bounds. So on that, if you call it the x and y axis, y goes from 0 to x. So y is equals 0 is actually this x-axis, and y is equal to x is this line, y equals x. So y goes from 0 to x is basically this region over here. And how is x varying? Well, x is going from 0 to infinity. So this, this process of shading out rectangles, basically vertical, tracing out these vertical lines like these to denote the area, is going on infinitely, because x is basically tending to infinity, right? Because of this outer integral. So that's our region. Now converting that to polar coordinates shouldn't be much of a challenge, because in our polar coordinates we only care about r and theta. So r, well, the distance, the farthermost you go from the origin is infinity, because x is going from 0 to infinity. So r is going from 0 to infinity, and theta, well, look at what angle this y equals x is subtending. This angle y equals x, if you probably were to use the inverse tangent or something like that, or just plain old common sense, is pi over 4. So we're actually going from an angle of 0 and then going all the way to this pi over 4 over here. So theta goes from 0 to pi over 4. Okay, so now converting our integral in terms of r and theta polar coordinates is, we want dr d theta, so the d theta should be outside. So theta is going from 0 to pi over 4, radius is going from 0 to infinity, and we have e to the negative x is r square cosine squared theta, y is r squared sine squared theta, and x is r cosine theta in the denominator. And this dy dx or dx dy doesn't matter, it's pretty much commutative. R is equal to r dr d theta by this Jacobian thing. I'm not going to show the working of the Jacobian, but you get the idea. So the r's cancel out nicely. We have 8 over square root of, well, it's not square root of pi, I'm sorry, it's just pi, it's just like regular pi. So 8 over pi times integral from 0 to pi over 4, integral from 0 to infinity. Using some trigonometric identities, this is going to be e to the negative r squared over cosine theta dr d theta. So we're first calculating, integrating with respect to r. So the cosine theta can be taken outside. So integral from 0 to pi over 4 of 1 over cosine theta, integral from 0 to infinity of e to the negative r squared dr d theta. So this inside integral is actually the Gaussian integral. I have made an entire playlist on that. So please don't tell me I didn't tell you what the Gaussian integral, why it was equal to square root of pi over 2. Please don't say that afterwards. Okay, so stuff cancels out nicely. 4 over square root of pi we have, and integral from 0 to pi over 4, 1 over cosine theta is secant theta d theta, and this is a pretty standard derivative whose derivation is simple, and you basically multiply and divide by secant theta plus tangent theta, and then you make a substitution. You eventually end up with a natural log of secant theta plus tangent theta as the antiderivative, evaluated from 0 to pi over 4. Okay, so 4 over square root of pi, and natural log of, well, secant of pi over 4, secant theta is 1 over cosine theta. Cosine of pi over 4 is 1 over square root 2. So secant of pi over 4 is square root 2. Tangent of pi over 4 is 1. Minus natural log of, secant of 0 is 1 because of the cosine, and tangent of 0 is 0. So this is natural log of 1, which will go to 0. So our final answer is 4 over square root of pi times natural log of square root of 2 plus 1. Okay, that is supposed to be our I1. But the thing is, we can actually represent this in a way more classy manner. And when I mean classy, I mean really classy, in terms of some well-known functions. So if you have y is equal to sinh of x is equal to e to the x minus e to the negative x over 2. So what you do is you basically have y equal to everything, make everything into positive power. So e to the 2x minus 1 over 2e to the x. Rearranging stuff, 2y e to the x is e to the 2x minus 1. So we have e to the 2x minus 2y e to the x minus 1 is equal to 0. And we actually have ourselves a quadratic because e to the 2x is e to the x, the whole thing squared. So using the quadratic formula, e to the x is equal to minus b. So minus 2y is 2y plus or minus square root of b squared, which is 4y squared, minus plus 4 divided by 2. So stuff is going to factorize out. So if y plus or minus y squared plus 1. If you factorize out the square root of 4, which becomes a 2, and then 2 cancels out everywhere. So e raised to x is equal to this. Now take the natural log on both sides. So x is equal to natural log of y plus or minus square root of y squared plus 1. Now the thing is, you can't have a negative argument for the natural log. So just to avoid the risk of this inner quantity being negative, let's eliminate the negative root for now. So we have natural log of y plus square root of y squared plus 1. We just eliminate the minus from the plus or minus. Now what you do is x, we can trace x to be sinh inverse of y. So basically sinh inverse of y is equal to this. Now interchange variables, convert y to x. So we have sinh inverse of x is equal to natural log of x plus square root of x squared plus 1. Okay, and if you plug in sinh inverse of 1, you have natural log of 1 plus square root of 2. And that's exactly what we have over here. So this I1 can be written as 4 over square root of pi times hyperbolic sine inverse of 1. How cool is that? Okay, so to finally conclude stuff, um, we have the original I is equal to I1, which just turned out to be 4 over square root of pi times sinh inverse of 1, and I was just equal to integral from 0 to infinity of error function squared of x over x squared dx, which has an approximate value of 1.98905. How nice is that? We actually could tackle a complicated function like this error function that we started with. So that's it for this video, guys. I hope you really enjoyed this. This was a really interesting and unique one where we dealt with non-elementary functions whose antiderivatives, strictly speaking, do not exist. So yeah, we got a pretty neat answer involving the hyperbolic, inverse hyperbolic sine. So yeah, before I go, please like, share and subscribe to my channel, guys. Recommend me to your friends. Spread my word in the math community or any place that is related to the stuff I do. And in the meantime, stay home, stay safe, keep doing math, and don't forget to peace out.